Hello and welcome to the Wednesday meeting of this activity, um, Physics Without Frontiers in Guatemala. And today we have the participation of Juan Miguel Arrazola from Xanadu. Juan Miguel is currently the lead of the quantum algorithm team at Xanadu. Xanadu is a quantum computing company located in Toronto. The motto of Xanadu is to bring quantum computers to people. And Juan Miguel holds a Bachelor in Science from University Los Andes in Colombia, and Master in Physics from the University of Toronto, and a PhD in Physics Quantum Information from the Institute for Quantum Computing. He worked before at the Center for Quantum Technologies in Singapore, and he joined Xanadu in 2017. So thanks, Juan Miguel, and welcome to this activity. Please, you can start when you're ready.
Okay, I am ready. Thank you so much for the invitation, everyone, and Marco especially. It's my pleasure to be here. It's great. I really like the vision and the philosophy of this event, and it's something that, to the best of my ability, I try to participate in, sharing some of the work, some of our insights, and it is something that it's important for us at Xanadu that, despite being a company, right, we still publish our research, we still share some of our tools, we still make software open source. It is important that the technology, the insights, the innovations that occur due to our efforts are available to people as much as possible. And of course, that includes occasionally giving talks and sharing some of those insights. It's great to be here, and I look forward to hearing your questions and interacting with you. You can feel free to do that during my talk, but of course, also at the end of it, I'm happy to take some questions. I apologize, I reused these slides, and I have only ended from a previous talk that I gave. But regardless, we'll be talking about quantum chemistry with PennyLane. PennyLane is one of the quantum software libraries developed by Xanadu. And I will be giving the talk in English just because I'm much more comfortable speaking technically about science in English. Hopefully it will be understandable, nevertheless. But without further ado, I'd like to get started. And I want to talk about quantum chemistry. In my experience, people working in quantum computing, quantum information, quantum technologies don't always have the deep background in quantum chemistry. Certainly in my case, I've had to learn it over the past year or so. So I do like to set that stage by talking about some of the basic core principles and how they connect to quantum algorithms to tackle problems in quantum chemistry. And the first thing that I want to say is that often we use terms that try to encompass many things together, big umbrella terms, right? So quantum chemistry actually stands in practice for many things. And maybe the unifying theme is that this is about understanding the structure of matter. So when you have fundamental particles like the protons, neutrons, electrons that form atoms, these atoms themselves can form stable phases of matter, right? Typically in quantum chemistry is associated with the study of molecules and how molecules form and break potentially in chemical reactions. But there are different configurations that are important. Clusters, which maybe not so big, but also solids. So this is closer to materials science, but even things like surfaces, graphene, and so forth. So actually, a lot of the concepts that I will be discussing, even though we refer to them as quantum chemistry, they more generally apply to understanding the structure of matter, right? And something that is key about this problem, how do we understand the structure of matter, is that we know the basic rules for centuries, right? It's still governed by quantum mechanics, and we know the interactions due to fundamental forces, especially the electromagnetic force. And we know that all these systems can be described by a Hamiltonian, and we can obtain all properties of interest by understanding the wave functions that describe the systems, which itself can be obtained by solving the Schrodinger equation. So we know how to do this, right? But computationally, achieving this is intractable, right? This is just not possible. We cannot solve the Schrodinger equation exactly, even for relatively small systems. So a lot of the challenge, especially computationally, is developing methods to tame this problem in one way or another. And so we will be discussing what these look like. They typically look like approximations of different forms, and there's a fundamental one, and you'll see this being mentioned in the majority of introductions to papers in quantum chemistry and quantum computing for quantum chemistry. It's a very simple idea. It's saying, look, it's already really complicated to deal with systems completely general as quantum mechanical systems, and understanding what's going on with the nuclei makes things very difficult as well. So we're going to make an approximation where we're going to say, you know what, the nuclei are so much heavier than the electrons that we're simply going to treat them as point particles, fixed at some given positions. These are the positions are denoted by this capital R. These are the nuclear coordinates, and they will have some charge associated to them, and therefore they'll generate some Coulomb potential. Right? And what this allows us to do is to decouple the electronic and nuclear degrees of freedom. So mathematically, this is saying that the wave function describing the systems is essentially a product form, right? So we can decouple the degrees of freedom of the nuclei and the degrees of freedom of the electrons and focus only on the electrons, right? We clamp the nuclei at some coordinates, the nuclear coordinates are, and we associate some potential generated by those nuclei, and then we ask the question, what happens to a system of interacting electrons living in that potential? And this is what's known as an electronic structure calculation. And you'll hear that term being used all the time in the context of quantum chemistry, electronic structure calculations. And this is just a term referring to the fact that we are treating only the states and properties of electrons. Right? This is both a very good approximation in practice. So the discrepancies that you get from true values by making this approximation are very small. So you get really high accuracy even within the approximation. But secondly, typically it's electrons that are responsible for the properties that we care about. They're responsible for forming bonds. They're responsible for conductivity of materials, etc. So it's a great approximation, and it allows us to focus on the thing that we actually care about. Now, so now we reduce the problem to the electronic structure problem, right? And how do people in practice tackle this task, right? And there are many techniques, but roughly speaking, they can be categorized in two main strategies. The most widely used, most successful one is density functional theory, or DFT for short. This is an area that I still have so much to learn on, and it's fascinating, and it's very different from kind of the mentality that I have become accustomed to developing and thinking about quantum mechanics. But I'll give you a quick overview of what DFT does. The key idea is that instead of dealing with the wave function, you deal with the electronic density. And the electronic density is simply the probability of finding at least one particle in a given region of time, of space, a certain region of space. So it's a function of just spatial coordinates. The electronic density is therefore a much simpler object than the wave function, right? And the idea is that you cast every single calculation that you want to make in terms of the electronic density. Because it's such a simpler object, and because of other approximations that go into place, you can actually potentially simulate very large systems, right? Especially in materials, where some of the electronic effects are not as strong. But underlying this method is the use of approximations. So essentially what happens is that you say, look, electrons have correlations that are very important, and they're not going to be captured necessarily in this approach of DFT. We're actually going to treat the particles as independent particles with some electronic density, living in some potential. And the idea is to add some potentials that replace the effect of the electronic correlation. This is known as the exchange correlation potential. And we don't know what those exact terms look like, so people rely on approximations to this contribution. So it's an approximate method by construction, but there's no simple rule that tells you when it will be a reliable approximation or not. It's a very complicated thing to figure out. And importantly, there's no systematic route to improvement. It's not like a perturbative approach where you have an approximation, but you can kind of improve it and get better. It's not really the case. So in practice, using DFT is as much a science as it is an art, where you have a lot of freedom in choosing different strategies, different approximations, different tricks, and people try to navigate those as best as possible to get the best possible outputs from their calculations. The advantage being that overall, the complexity of carrying out these methods is relatively low. It's a very efficient method, and it actually works really well in practice in many cases, has also a lot of drawbacks. The other approach is to deal directly with wave functions, right? So we're trying to somehow represent the many electron wave function of the system. And by doing so, in principle, we have access to all molecular properties. With DFT, that's not always the case. You usually try to write down certain quantities of interest, like the energy in terms of the density. It may not allow you to compute anything that you want so directly. With the wave function, in principle, you can extract any information of the system. And they rely on approximations as well, but they can actually be improved systematically, right? So we can always get better on their approximations that then lead to higher and higher cost. So it's an accurate, very accurate approach, which is amazing. But as a consequence, it's extremely computationally intensive, right? And therefore limited to very small systems. Even with basic approximations, it becomes expensive very quickly to do so, right? However, these wave function-based approximations and approaches are a natural approach for quantum computers, because essentially the idea is that the quantum computer can directly represent the wave function of many electrons in terms of some state of many qubits. And we'll discuss how that's done in future slides. These are the main methods, right? So how exactly? So we're going to be focusing on the wave function-based methods, again, because this is essentially what quantum computers are trying to do. But it's important to understand that DFT is actually the most widely used tool currently for both quantum chemistry and material science. And there's different ways of doing this. We are going to be focusing, for the sake of this talk, in second quantization. And here, the idea is that the state of many electrons, interacting electrons, will be represented in the occupation number basis, also known as a Fock space. Right? Those of you that maybe have a background in quantum optics or know about quantum optics, it's very similar, right, to how we represent states in bosonic systems. But these are, of course, fermions. And so there's this notion of having then a collection of orbitals. You can think of orbitals as single particle wave functions. And we simply state whether these orbitals are occupied or not by some of the particles. Right? So we have a collection of n orbitals. And the state is simply a tensor product of systems representing these orbitals, where we specify whether that orbital is occupied or not. Right? So you can think of something like these orbitals themselves having different energies and having associated different energy levels. They are more generally spin orbitals. So for each spatial wave function, you can have 2 degrees of freedom. Your electron can have spin up or spin down. And therefore, we can occupy these orbitals of different energy by simply essentially putting particles in those orbitals. Right? So again, this is very quick, what I'm saying right now, but it's introducing some of the jargon and some of the terminology. And once we have that specified, then there's a core standard method called the Hardship Method that is actually very important as an initial step in quantum algorithms for quantum chemistry. And there's different ways of thinking about the Hardship Method. I'm going to share the way that I like to think about it, where the idea is the following. Ultimately, what's going on is that we're treating the electrons as being independent particles. Right? So we are neglecting the effect of correlation between them, which is very important, but we're neglecting it. And we're treating the electrons as essentially interacting with some mean field generated by the other electrons. So it's a little bit similar in spirit to what DFT is trying to do, which you're trying to introduce some additional potential while still treating systems, the particles, as being independent. But more precisely, what we're saying is we're going to assume that the approximate state of our system is going to be what's called a single slated determinant. So there's a mathematical definition for it. It's this determinant that you see here, where you have a collection of orbitals, and you essentially make sure that it's properly anti-symmetrized to respect the exchange statistics of fermionic systems. Right? But in the occupation number representation, what we're saying is simply that we have a collection of orbitals, and we're going to be occupying some of those orbitals, and that's it. More generally, you can have a superposition over different patterns of how you occupy the orbitals, and that's a general state of the system, and that can account for correlation. You can have entanglement between electrons occupying different orbitals, so entanglement between the orbitals. But we're going to neglect that. We're going to say we have a single such state, right? It's just a product state, and that state is something that we call a Slated determinant, ultimately. Right? So the idea is, so if we have a state where we have a collection of orbitals, and we simply occupy the lowest energy such orbitals, what we reduce the problem to is to optimizing what those orbitals actually look like in such a way that we minimize the overall energy, right? And so these are the this is the problem. So we have some state, it's a single Slated determinant. We compute its expectation value with respect to the Hamiltonian, and that state will be defined with respect to some specific set of orbitals, and we minimize over those orbitals, right? And by doing that, and you can do this in a way that I will explain in future slides, you obtain the Hardship energy and associated, so the minimum energy, but also energies associated to each of the orbitals because you have optimized these orbitals. And then the Hardship state is simply one in which each particle is occupying these optimized orbitals such that you're occupying the lowest energy such orbitals, right? So in other words, we're simply saying we're going to try to find the state that is has no correlations between the electrons. So it can be written down as a product state such that we have the particles occupying independently each of the orbitals of lowest energy, and we're trying to optimize what those orbitals are. That's the Hardship method. So it gives you a good basis of orbitals to work in. And here's the detail of how that works in practice. Essentially, we use this technique called the linear combination of atomic orbitals. So the orbitals described in the system, they are called molecular orbitals. So they are typically spread out over the entire molecule, as you see in this example on the right. We express them in terms of atomic orbitals. These atomic orbitals are centered around each atom, right? So the molecular orbitals that we care about are linear combinations of the atomic ones that are centered, right? And what we're trying to do is we're trying to optimize the coefficients that describe that linear combination. Right? So that's the goal, and that's how we find the optimized orbitals in the Hardship method. We're trying to find the optimized parameters, the coefficients C, that describe that linear combination. Now, to do that, we actually express the atomic orbitals in some bases, and therefore they're also given by some linear combination of these basic functions of this form. Right? So there will be some contraction coefficients, A sub I, and there will be some other more elementary primitive basis functions. Here I'm using psi to represent them. Typically, this will be Gaussian functions. Right? So in other words, the molecular orbitals are a double linear combination. They're a linear combination of atomic orbitals, and the atomic orbitals are linear combinations of typically Gaussian basis functions. And so the goal is to find the coefficient C that minimize the energy of the single Slated determinant, right? A state where you're simply occupying some of the orbitals. And you could imagine different ways of tackling this, like a direct optimization, but it's been known for a very long time that the solution to this optimization problem can be reduced to solving what are called self-consistent equations. These are essentially an eigenvalue problem, except that the matrix you're trying to diagonalize depends also on the coefficients that you're trying to find, and hence the term self-consistency. That's not too important. What's important is that it's given by this equation that you see here, Fc equals SCE. E are the energy, C is the matrix of coefficients, and you have this matrices F and S, known as the Foc matrix and the overlap matrix. What's important is that the definition of these matrices ultimately depends on some integrals over the orbitals, right? And therefore, there will end up being some complicated linear combination of integrals over Gaussian functions. And that's ultimately the reason to use Gaussians, is because there exist closed form analytical solutions for Gaussian integrals. So we can actually express the construction of these matrices without having to do any integration whatsoever. We just know the formulas for the values that are obtained. And that's the advantage of using Gaussians. Now, the reason to do it is that what we're doing is we're essentially saying, like, look, our state will generally be some linear combination of states in a system that's interacting, right? What the Hardship method is trying to say is, like, if you imagine that big linear combination, you try to find some basis of the orbitals, right, such that there is one single state in that superposition, actually, that has the largest possible overlap, right? So in other words, the way to interpret wave function after undergoing the Hardship method is that it's essentially saying there is one big component of the properties of the system that are given by some contribution of non-interacting electrons, plus some additional contribution from the interactions. And that's the part that we're missing from Hardship. That's the fact. That's what we want to find out with potentially other methods. These other methods are known as the post-Hardship methods, right? And typically what happens is that, I mean, it depends on the system, but the Hardship-Fock approximation is very good. If you look, for example, at the energy, it actually accounts for a lot of the total energy. The problem is that that remaining energy is actually crucial for understanding the behavior of systems for two main reasons. First, we don't typically care about absolute values of energies. We always care about differences in energies, right? And so the contribution from the non-interactive component can be very similar in different configurations. And therefore, those differences are actually dominated by the correlations. And one way that this manifests itself particularly is in the fact that the Hardship-Fock method doesn't explain how molecules can form bonds. And so you won't really find correct expressions for things like binding energies. Right? So definitely the effect of correlations, even though it seems small, is actually very important for understanding the behavioral systems. And therefore, the Hardship-Fock method is just not sufficiently accurate to get any meaningful results for understanding the structure of matter. But it can be a good starting point. Right? Now we start connecting to quantum computing. And something that we'll have to do is to represent the wave function of a system of interacting electrons on a quantum computer. And there are different strategies of doing this, but essentially the main idea is that we will be mapping two things. First, states, right, of fermionic system, two states of qubits, right? And this is achieved by what are known as fermionic to qubit mappings. There are three main ones: the Jordan-Wigner parity encoding and Bravik-Kitaev. Essentially, what you have to be careful with is both representing the occupation numbers, but also parity effects, which are dealing with exchange statistics of fermionic systems. Right? In practice, Jordan-Wigner is the most straightforward and simple to understand. What we do is that we associate each orbital to a qubit, and then the qubit states 0 or 1 denote whether their orbital is occupied or not. Right? So very straightforward. Qubits represent orbitals, and qubit states represent whether the orbital is occupied or not. It's very direct representation of the occupation number representation. And in Jordan-Wigner, all the parity effects are then absorbed by the operators, essentially, right? And so what we do is it's often useful to work solely in terms of the fermionic creation and annihilation operators. And then there's simply a rule in how to map them from the fermionic representation to the qubit representation. And it looks something like this. You have some action locally on the qubit and therefore orbital that the operator is actually defined on. This is the x sub p plus I y sub p term. You can think of this as kind of a qubit ladder operator, but you also have to take into account exchange symmetries that introduce these sigma set, these are Pauli matrices on other qubits. But essentially, we represent states very similarly to how they do in occupation number representation. And then we map observables and operators according to a specific rule that ensures that they have the same effect and the same exchange symmetries. And that's essentially how we represent states of fermionic systems in terms of states of qubits. Right? Now, we're getting closer to quantum algorithms. Right? The main goal is to find methods for the quantum computer to directly prepare wave functions of these systems, specifically post-Hardship-Fock wave functions. And maybe I should have said that something that's really nice about this encoding is that the Hardship-Fock state, which is simply saying I'm occupying these orbitals, and it looks something like this in the bottom right. When mapped to qubits in the Jordan-Wigner representation, it's exactly a computational basis state. So it's very simple and straightforward once you have the optimized orbitals to have initial states that represent the Hardship-Fock state. Right? And then the idea is that potentially you have quantum algorithms that are preparing wave functions represented by the qubits that take into account the effects of electronic correlation. Right? So we're trying to create a post-Hardship-Fock wave function. There are many methods for doing this. Right? Some that I'm not including are things like imaginary time evolution, Krylov subspace methods, adiabatic quantum computation. In practice, there are two main methods that people focus on. Strategies like VQE, aimed at optimizing some variational circuit, So essentially, we start from a representation of the Hartree-Fock state, and then we apply some operations to generate the other contributions that give rise to the electronic correlation effects. Right? So this is the main strategy of VQE, and then we try to optimize how these gates are acting on the system. There's also variational algorithms are, of course, heuristics. So we don't have any guarantees of their performance. And it's also very hard to actually deploy them for realistic systems because neither our simulators nor existing quantum computers allow us to do it, right? So there are definitely heuristic approaches. On the other side of affairs, there are more advanced algorithms that we can only realistically run on fault-tolerant quantum computers, like quantum phase estimation, right? And so there are more sophisticated methods of both preparing these wave functions, but importantly, extracting information and properties from the wave function. And that second point, as a side note, is actually absolutely crucial in this system. So quantum algorithms need not only to worry about how to prepare states of systems, they also need to worry about how to extract information from those systems. And that's not always easy, right? In fact, in my expert opinion, this is the main difficulty of variational approaches, is that extracting and computing expectation values, especially for molecular Hamiltonians, is very inefficient. It's a big challenge. But this is the main idea of quantum algorithms for quantum chemistry, right? And people have figured out how to do many things, especially the type of calculations that are actually relevant in practice. A lot of properties of systems can be reduced to computing ground state energies. So this remains one of the most important tasks to be solved in quantum chemistry, and again, in material science and other areas of application. And we understand how to do it both with variational approaches, with quantum phase estimation, and alternatives. But we also know how to compute excited states, which are important in certain cases, compute things like nuclear forces and the geometry of molecules, transition states and chemical reactions, reaction rates, and even look not just at the electronic structure, but also vibrational structure of molecules, understanding how molecules vibrate, especially when stimulated by light, for example. And people have developed some of these techniques. So we have participated to some extent in these efforts as well. But they all rely on similar strategies ultimately, right? You're using the quantum computer to prepare a specific state, and then having some strategy to extract information from that state. That's essentially the background on quantum chemistry. I know it's very fast, and I'm trying to cover a lot in a very short period of time. So I'm not expecting everything that I said to be 100% clear, but hopefully some of the main terms become a little bit more familiar. And they are essentially the foundation for starting to think about both quantum algorithms, but specifically quantum software for quantum chemistry, which is what I want to tell you about now. But it's a great moment for questions, if anyone has any. OK, then I'll keep going. So I want to tell you now how to use PennyLane to tackle problems in quantum chemistry. So again, what's PennyLane? It's the flagship quantum software library developed by Xanadu. You can hopefully many of you are familiar with it, but if not, I do invite you to take a look. It's a library that started as specifically being tailored at quantum machine learning, but really we are growing it to be a general purpose library for all of quantum computing needs. And part of the role that my team plays is precisely building functionality directed to quantum chemistry, but more generally quantum algorithms. Right? How do we solve problems using our software? Right? And we do have a big focus on quantum chemistry. This is work, and you can find the information on the website. We have great documentations, great tutorials, and really the library is fantastic, and I do encourage you to take a look. Something that we've been working on is precisely on quantum chemistry functionality. And I also invite you to take a look at a paper that was released last week, actually, really encapsulating the efforts of over a year in developing all this functionality, mostly by the team at Xanadu, but also from collaborators in industry and academia. It's also a great, or our goal was to make it a great resource for beginners, for people that are working in quantum computing, quantum information, but are maybe not so familiar with quantum chemistry. There are many resources out there, but they are not always easy to digest. So the goal of this paper partly is to provide all the technical concepts. A lot of the things that I tried to convey in the beginning of this talk are well summarized in this paper. So I do invite you, if you want to learn more, not only about how to use the software, but about quantum chemistry and quantum computing. We did put a lot of effort in trying to be concise, but also accurate in explaining the main concepts. So a lot of what I will be discussing here is also captured in this paper and, of course, in our online documentation. First, before I tell you what we can do and how we do it, I want to tell a little bit about the way that we think about implementing the software. One of the things that I've learned is that it's part of the hardest questions you have to answer when you're actually developing production-level scalable software. Is not what you do or how you do it, but how do you present it to the user, right? How will people interact with your functionality in a way that makes for a great product, right? And there's different ways of doing this, and there are different strategies. I will share our vision of doing this. We definitely target user friendliness. So we want this to be a tool that a lot of people can use, and that the barrier of entry is as low as possible. And one way to do it is to produce a lot of educational material. So we put a lot of effort in having great documentation, having a lot of great tutorials, writing technical papers, right? Such that they overall minimize the reliance on technical knowledge of both quantum chemistry and some other classical packages. Central to everything that happens in PennyLane is the ability to differentiate through workflows. So in every step of quantum chemistry functionality, we ask ourselves the questions: how can you actually compute derivatives over every single object, every single function that is happening here, right? And something that we do is that the way we like to target user friendliness is not by doing everything for the user, such that you just take something that's built and apply it directly in a way that then may be easy to use, but very inflexible, and you may not be understanding while you use it, but instead putting an emphasis on building blocks, right? On strong building blocks, and then give you the flexibility to do anything that you want. And this is as opposed to having some black box that just, implement algorithm, and then you get the output. And you don't know what's happening, and you don't know how to change anything about the algorithm, but you get the answer. So that's not what we want. We want to give people the tools to build things themselves, right? And then we support that by having great documentation and great material to explain how to use these tools. So that's a unique, I think, vision of how we actually write code, how we develop the libraries, right? So again, in particular for quantum chemistry, you find a lot of material on tutorials, from basics to some more advanced techniques. So again, for those of you that are interested in this direction and in this area of research of quantum algorithms, I do invite you to take a look. Most of it is based on variational quantum algorithms because of their possibility of actually carrying out simulations and proof of principle experiments on hardware. And when it comes to quantum algorithms and when it comes to software for quantum chemistry, then I like to ask this question. So, where does quantum chemistry actually make an appearance, right? How are quantum algorithms for quantum chemistry different from quantum algorithms for anything else, right? And it's an interesting question. My answer to the question is that there are two main components. First, the Hamiltonian plays a crucial role, right? So understanding how to build the Hamiltonian, how to maybe transform and manipulate that Hamiltonian, how to make operations on that Hamiltonian, how to compute properties of that Hamiltonian. That is really central. And if you're a beginner and you want to maybe tackle some problem, that's the first obstacle you'll have to face is, well, how do I build this Hamiltonian representing the molecule that I want to study, for example? So that's something that you have to put in a lot of emphasis on, is how to both build and manipulate Hamiltonians. And of course, the second is that we, like I mentioned, roughly speaking, the goal of quantum algorithms is to prepare states that represent ground state excited states of molecules, for example, but other systems. So how do we actually do that? How do we apply the correct gates? How do we apply the right operations that allow us to build the correct states on something else, right? So we have to inform the way that we construct circuits in such a way that they take into account the specific structure and properties of quantum chemistry. So let's take a look at how this is achieved. The strategies for building Hamiltonians are understood. They're straightforward. Essentially, what happens, this expression that you see here, I'm using A instead of C to represent the fermionic operators here. It's kind of a typo, essentially. but these are creation and annihilation fermionic operators acting on orbitals, right? And these quantities HPQ, HPQRS, these are integrals over the orbitals that, again, we will normally have optimized using the Hardship method. So ultimately, what you need to do is to implement the Hardship method, obtain the optimized orbitals, and then compute some integrals over those orbitals. And that's how you build a Hamiltonian. This is a known problem, and so the user doesn't have to go through all these details, meaning that we've put efforts into making sure that you can build these Hamiltonians very easily. Right? This is something that you don't need to understand too much. So the simplest way of building a Hamiltonian in PennyLane is simply to have a list of the atomic symbols representing the atoms in the molecule, an array of nuclear coordinates telling us the optimized geometries of the positions of the nuclei in the stable configuration of the molecule. And that's all the information that you need, plus some default choices of other parameters. I will talk about it in a moment, to actually build the molecular Hamiltonian. So if you want to get started off the bat and construct a Hamiltonian and then start analyzing properties of that Hamiltonian, for example, trying to compute some ground state of the Hamiltonian and the corresponding energies, it's very simple to do so with just a few lines of code, right? And besides having the explicit list of nuclear coordinates, you can also load them from standard packages if you're familiar with how this usually works in classical methods for quantum chemistry. Of course, there are a lot of other options on how to build Hamiltonians you have to be careful with. So you may have a system that has charge. You may be looking at different spin sectors. This is something that's captured by this term, the multiplicity. There are these basis functions that are used to represent the orbitals. So you may be working with different types of basis functions, different packages that may be using performing the Hardship calculations. You can look at active spaces. So there's a lot of, and even these mappings that I mentioned from unit to qubit. You can play with all of those. These are kind of options for advanced users, and they can happen relatively straightforward as well by simply passing the corresponding keyword arguments. Right? Additionally, if any of you are actually already comfortable working with open fermion Hamiltonians, it's very simple to take that Hamiltonian and convert it into a PennyLane Hamiltonian that allows you to then carry out subsequent computations. There's also support for other observables. So you can obtain qubit representations of the total particle number, of total spin, and even spin projections. And that can be useful in certain cases, for example, when analyzing excited states. It's straightforward to support this. Right? Now, so in other words, dealing with the Hamiltonian is very important. It's a very important part of workflows for quantum chemistry and quantum algorithms for quantum chemistry. But it's in a way also a solved problem. This is something that we just know how to build Hamiltonians. And so we simply provided all the functionality such that it's relatively simple to build the Hamiltonians, even when you want to have some advanced features on how to define them. Now, more interesting is how do you carry out quantum algorithms? And so I want to spend some time talking about the notion of excitations. Right? So remember, we're working in the Jordan-Wigner mapping, where each qubit is associated to an orbital, and the state of the qubit represents whether orbitals are occupied or not. So this is an example with a system of 6 orbitals, spin orbitals. So we have 3 spatial orbitals, each of which can hold spins that are either spin up or spin down. And they're ordered in energy from left to right. So the state on the left, the 110000, is representing a state of 2 particles, 2 electrons, on 2 spin orbitals that have the same energy but opposite spin. Right? Now, other possible basis states of the system will have different configurations of how the electrons are actually occupying different orbitals. And what we can do is that we can associate that state and represent it in reference to this reference state by identifying ways in which these particles are excited with respect to their occupation in the reference state. So for example, this state here that you see on the right, we're representing a single excitation from the reference state. The state 100100 is now saying, well, we're taking the spin down electron in the lowest orbital, and we're exciting it to a new orbital, right? But we're doing it for a single particle. Right? And so we refer to this state as different by a single excitation from the reference state. And you can imagine that you can keep going, right? If you have a state now where the particles are occupying different orbitals, maybe of higher energy, this will correspond to a double excitation. It's double because you're taking two particles and you're exciting them both. Right? In general, any state of any system can be interpreted as being a certain type of excitation from a reference state. Typically, the reference state is chosen to be the Hartree-Fock state. Right? So we can think of wave functions, which are states of many qubits, as being some superposition of potentially a reference state and excitations with respect to the reference state. So what we want to do is to build circuits that implement these type of transformations, right? In particular, in such a way that also respects some of the symmetries of the problem, in particular, the fact that we have a fixed number of particles. If you notice, all these states will have the same Hamming weight, the same number of ones. So we want to have, it's useful to have operations that respect that symmetry, that only map states with a fixed number of particles to other states with a fixed number of particles. And one simple way to do it is to think of this transformation here. This is a 2-qubit gate that is only coupling the states 0, 1, and 1, 0, right? And we can think of that as actually, if those 2 qubits correspond to different orbitals, right? Then what's happening here is that we're essentially coupling states that differ by a single excitation. Right? In the diagram that you see on top, imagine that what we're doing is we're taking this spin-up electron and exciting it to a higher energy orbital, right? So we can apply this operation on the first and third qubit, and what we're doing is that we're coupling these 2 states that you see below, right? This is therefore effecting a rotation in a 2-dimensional subspace defined by states, 2-qubit states that differ by a single excitation, right? And Givens rotations is the name given to rotations on 2-dimensional subspaces of larger subspaces. So this particular gate is an example of a Givens rotation. Right? And we have a tutorial that explains this in more detail. Then you can start increasing the degree of the excitation. So similarly as what we had here, where you're rotating this subspace between states that differ by a single excitation, you can now have rotations between states that differ by a double excitation. Right? The states 0, 0, and 1, 1 versus 1, 1, 0, 0, they differ by taking 2 of these particles and exciting them to different orbitals. Right? So we're coupling states that differ by a double excitation. And maybe you can start seeing already that by applying these type of gates, we can start from a reference state, adding contributions with respect to new states that differ by a certain degree of excitation. Right? And something that we prove in this paper that I'm referencing in the bottom is that you can actually build any particle conserving state. So sorry, any particle conserving gate, any particle conserving unitary in terms of these Givens rotations. Right? In particular, if you take a controlled single excitation gate, which is simply the same single excitation gate that I have here, except that you have a more general U2 rotation, not just this orthogonal rotation, controlled on some additional qubit. So it's a 3-qubit gate that is actually universal for particle conserving operations. So for us, they are that building block that I referenced in the beginning that we put a focus on. We want to have great building blocks. So Givens rotations are the building block for building quantum circuits inside of PennyLane. Not only are they universal, not only do they have this interpretation of building the contributions that we actually care about, but they have other initial nice properties. That they're fast to implement. We know the compositions into elementary universal gate sets, and we know how to compute, for example, gradients very efficiently from these gates. So the idea is that we can build circuits using these excitation gates, and they are natively implemented in PennyLane as single and double excitation gates. So this allows users to build these circuits themselves, but of course, a lot of people have put a lot of efforts into studying specific techniques on how to define circuits, right? So there's the notion of ansatz for quantum chemistry. And so we also support them in the form of templates. So if you want to use a specific architecture or circuits that are aimed at quantum chemistry applications, then we support some of the main ones. The all singles and doubles is one that's based directly on this notion of Givens rotations. Actually, the gate fabric, and this is a paper from the team in Covestro and QC Ware, is also actually using in the background the notion of Gibbons rotations, but there are other more classic ones like unitary coupled cluster, singles and doubles. So users have both options. They can use standard templates or also design circuits themselves. And one way that you can design these circuits yourself is to use adaptive strategies. What happens here, and the main method here is what that's called adapt VQE, but in reality, it's a more general strategy where instead of having some fixed template, some fixed ansatz that you use for every single problem, given your problem, you're trying to find a good set of gates that actually contribute significantly in preparing the state that you want. And what this allows you to do is to have more efficient implementations. And this is useful particularly in tackling larger systems where you benefit a lot from reducing the depth of your circuits, right? And in fact, both in hardware and simulations, adaptive strategies typically are more efficient to execute. And so for my team, they are the preferred method for building quantum circuits, variational quantum circuits for quantum chemistry. And this is very simple to do in PennyLane because PennyLane allows you to compute gradients with respect to everything that you're doing. So the main strategy of these adaptive circuits approaches is that you select gates that lead to a large gradient with respect to the cost function, which is typically the expectation value of your molecular Hamiltonian. So how exactly you choose them, it differs between different methods, but you're always trying to compute the gradient with respect to the cost function for a specific gate, and then if it's large, you basically keep it, right? So that requires you to be able to compute gradients of gates, and this is something that PennyLane handles natively, right? This is like the thing that PennyLane is built around, is being able to easily compute gradients. So for example, you see here how we can compute the gradient in a single line of code just by calling qml.grad. QML is how we usually import PennyLane. So very easy, straightforward to create these adaptive circuits. And again, we have a tutorial dedicated to explaining how this works. Second, like I mentioned, it's not only about preparing state, but also about extracting information from these, right? When you're using the variational approaches, you have your state at the output. Maybe you've been successful and you've trained your circuit such that the output of that circuit is very close to the ground state, right? You still need to be able to compute the expectation value. And you don't want to have another complicated circuit, maybe with some auxiliary qubits as well, to be able to compute that. So in practice, what these strategies do, at least in hardware, is that they decompose the Hamiltonian into a sum of terms of local poly, so products of poly operators. They're often called poly strings or poly words, right? Where there's a lot of them, right? Even when you're using smart strategies, if n is the number of orbitals, then this might grow as n to the cubed, right? And if any of you have ever worked with quantum chemistry, you'll see that even for small molecules and simple basis sets, quickly the number of terms in the Hamiltonian explodes, right? So, so in simulators, you want to do something more clever, right? And something that we support directly. And if you're interested in using PennyLane for quantum chemistry applications, I do recommend that you use this method. Is to actually directly have a sparse matrix representation of the Hamiltonian and then compute expectation values directly as matrix vector multiplication. Right? So this example code here shows you how to do it. You compute expectation values of directly a sparse Hamiltonian representation of the Hamiltonian that you built above. Right? And what happens in the background is that this is a much more efficient way of computing expectation values, and it can vastly speed up simulations, specifically for simulations, right? This is not something that we can do in hardware, of course. So more of a recommendation, if you want to use, definitely try this approach. And once you have this, these fundamental components, fundamental ingredients, where we can construct Hamiltonians, we can construct circuits, and then we can compute expectation values and gradients of the circuits. That's all the machinery that you need to carry out different algorithms. So again, the standard thing to do is to compute ground state energies, but there's also strategies to compute excited states. There's the idea of obtaining potential energy surfaces. This is actually computing ground states for different nuclear coordinates of your system, and even looking at things like reaction rates for certain chemical reactions. And we have, again, tutorials to explain how to do this in most cases. Right? Now, but if you want to do more stuff, you need more tools, right? And a big part of this is the fact that you don't only care about the energy itself, but often also about the gradients of the energy. Here, we're thinking of the energy of the ground state energy and thinking of it as being parametrized by the nuclear coordinates, right? Remember that in the Born-Oppenheimer approximation, we're simply saying we're fixing the nuclei to be at certain positions, right? But we fix them. So in particular, we can change those positions, and those give rise to a different Hamiltonian, right? Because the essentially the Coulomb potential that they generate has now changed, right? They're in different positions. So we can always think of the energy as a function of the coordinates of the nuclei, and we can then look at taking derivatives of the energy with respect to the nuclear coordinates. The simplest example of why this is useful is that you may want to compute forces acting on the nuclei, right? And then this force is just related to the derivative of the energy with respect to the nuclear coordinates, right? At equilibrium, this force will be 0, and that's what defines the equilibrium geometry of a molecule. And so this is known how to do it, right? Essentially, you can reduce the problem, or let me rephrase it. So let's think actually not so much about computing forces, but about optimizing the geometry of molecules, right? And this is a strategy that's shown in this paper that our team wrote. What happens here is that you're thinking like, well, the molecule will be in a stable configuration when we minimize the energy not only with respect to the state, which defines the ground state energy, but also with respect to the nuclear coordinates, right? So that gives us both the ground state energy, but also the equilibrium configuration, the equilibrium geometry of the molecule. So cast that way, this is simply an optimization problem, right? But where we're minimizing not only over the coordinates, right, but also over the state. And in a variational approach, we're therefore optimizing also over parameters of that circuit, right? And the nice thing is that then we can think of this as a joint optimization problem, where we're simply optimizing both over the Hamiltonian parameters and the circuit parameters, right? And this requires us to be able to calculate gradients of the energy with respect to the nuclear coordinates. And this is done, and there are formulas to do it even for higher order derivatives. In the case of the first order derivative of the energy with respect to nuclear coordinates, this is given by the Hellman-Feynman theorem that basically tells you that this gradient is equal to the expectation value of the derivative of the Hamiltonian, right? Now, what most people do is to take a finite difference approach of this Hamiltonian. So you perturb the coordinates and try to approximate the Hamiltonian this way. And this is something that's natively supported in PennyLane. But something that we worked a lot on, and it's actually the main feature of the white paper that I mentioned at the beginning, is a feature that is new, and this is the first time that I'm talking about it in more detail to anyone, is actually a differentiable implementation of the Hardship-Foc method. So if you remember all the steps that I mentioned, where you have these Hardship-Foc equations, and you have all these integrals that define the Foc matrix and define the overlap matrix, and we have to solve this, all that entire workflow is something that can be written in a way that's compatible with the methodologies of automatic differentiation in such a way that it's possible to compute derivatives over the entire code, computing all these functions and ultimately computing the orbitals and the Hamiltonian, right? So, and if you remember, the Hamiltonian depends not only on the nuclear coordinates, the position of the nuclei, but also on some of the parameters of the orbitals, right? Maybe it's worthwhile to go back where we have these orbitals depending on exponents of this alpha I. These are Gaussians. We have some term that looks like e to the minus alpha I squared. So we can actually tune essentially the variance, the width of that Gaussian, but also these contraction coefficients, AI. Ultimately, these determine what the once you have optimized for these coefficients, C, this is what the Hardship-Foc method does. You can still also think about optimizing over the AI alpha I, right? So the Hamiltonian ultimately also depends on these basis set parameters. So what you would like to do is to have some workflow where you can actually optimize over your state parameters, but also all of the Hamiltonian parameters, right? And the direct native way of doing this is to simply have a implementation of the Hardship method that is compatible with automatic differentiation, such that we can actually compute derivatives over every single parameter that appears in that computation, right? So I'll give you a quick overview. Again, all this code that I'm sharing, I'm not expecting you to follow it, but to give you an idea of how things work, right? But essentially using this differentiable Hardship method, again, this is a unique feature in PennyLane. No other quantum software library allows you to do this. You get exact gradients of the Hamiltonian, right? And they allow you to do specific type of workflows that are only really possible when you have this functionality. So in particular, what I'm showing here is now a different way of constructing Hamiltonians, where we're also specifying geometry, and we're also specifying some symbol. This is the hydrogen molecule, right? But we're also initializing these basis set exponents and the coefficients, the contraction that define the atomic orbitals, right? Then there's a different strategy here where we have these molecule objects, but then having these molecules and having specified that the geometry, the exponents, and the contraction coefficients are differentiable, right? We can generate a Hamiltonian that is now going to be differentiable with respect to these parameters, right? And it allows us to do things like natively compute the forces, right? So what this example code is showing is a situation where we have some circuit that is actually generating the ground state. We have previously optimized that we have just this one double excitation gate with this angle that prepares the ground state. So we have a circuit that computes the expectation value of this state with respect to the Hamiltonian that we defined previously, right? Now, what we do is we have a function that returns that energy, giving some molecule that we have defined. And then in just one line of code, you can actually compute the gradient of that energy with respect to all the arguments of the Hamiltonian that we defined previously, the geometry, the basis set exponents, and the contraction coefficients. And I'm wrapping up the talk soon. I know we're running out of time, but it's just a simple additional line to get an exact gradient for the energy with respect to all these arguments, right? And what they allow you to do, and again, I'm not expecting you to follow this, but to get an idea of things that we can do with PennyLane and only with PennyLane, is now we can have workflows where you're optimizing over everything, right? We're optimizing over our system, our state, by optimizing the gates against a simple example here, which is some double excitation Givens rotations. But we're also then computing gradients with respect to the circuit parameters, with respect to the nuclear coordinates, the exponents, and the contraction coefficients. So what this allows you to do is, again, by computing forces, you can optimize geometries of molecules. By taking high-order derivatives, you can also construct Hessians and therefore obtain vibrational modes and vibrational frequencies of molecules. But by optimizing the basis set exponents and contraction coefficients, it's actually a way of minimizing the energy in such a way that you get, so therefore you get better estimates, even though you're using a very small basis set, not by working with a larger basis set that requires having more qubits, right? Maybe I didn't explain this so much, but people often work in the way they express these atomic orbitals as a linear combination. You often work with just a few of these Gaussian functions, right? And so that's an okay approximation, but it's not very accurate. If you want to have more accuracy, you need a larger basis, right? And larger basis actually leads to a larger number of qubits, which means that the computations are more expensive. So instead, something that you can do to tackle that problem is actually optimize over these parameters so as to also reduce the energy. And this makes sense because often the values that people use are optimized to work in the general case, not in a specific case. So you can actually get a benefit by optimizing them for the specific molecule that you're working with. This is very much a prototype kind of beta functionality that we have in PennyLane. Definitely encouraging people to try it out and to give us feedback. But it is something that is both uniquely available to PennyLane users, but also allowing to carry out specific and more interesting, more advanced types of calculations. And we're definitely looking for feedback and constantly working on improving this as well. So I believe that's the end of my talk. Thank you so much, and I'm happy to take questions from anyone.
Thank you very much, Juan Miguel. And we have some questions, and I'll let you know first. The first one, what is the scalability of that quantum computing has achieved to be able to solve problems such as the helium atom.
The helium atom.
Yes, helium atom.
Okay, maybe I can answer the question. So the helium atom is not a complicated one. It's also not a very interesting one in the sense that there are more challenges when you look at molecules rather than single atoms. So I haven't really seen too many people working with helium. But it's a simple system, right? So it's not particularly challenging. You could definitely tackle it. So maybe I'll try to answer a more general question, which, what about the scalability of these approaches, right? So I should say I'm very much aware of all the limitations of variational approaches. I'm not a big fan, actually, not really putting my bet on the fact that we can use things like VQE to outperform anything that we can do classically. There are two main problems. One that is a bit technical, I tried to allude to, is the fact that essentially to have a high accuracy, we have classically, there's a lot of methods that give you approximations, like I tried to say. Right? There's both wave function based and DFT methods that give you good approximations. So what people are really lacking is higher accuracy. Right? Now, to get high accuracy in the calculations, you also need a good basis set. Right? So you want, for example, in this linear combination of atomic orbitals approach, you want that the way that you express atomic orbitals is over a very large set of Gaussians, right? Typically. Now, in practice, what that leads to is a very large number of qubits, right? So if you want high accuracy, you need a lot of qubits, and that's definitely a big challenge. Moreover, we still don't understand very well how to construct really, really good quantum circuits for larger systems. People use a lot of heuristics, like the couple clustered and some of the gate fabrics, our own approach of all singles and doubles. But we don't have any guarantees of how well they work. So we don't know if we can actually prepare good ground states. But the most important thing, and if you learn anything from this talk, I'm happy if it's this one, is that the strategies for computing expectation value, which are needed, for example, to obtain the thing that you want, which is an estimation of an energy, but also to optimize, has the huge problem that this scales very badly. So the number of terms that you have to estimate grows very quickly with the size of your system, right? And moreover, the number of samples that you need to estimate each term also doesn't scale very favorably with that number of terms. So you end up, and there are papers that do this in detail, so when you analyze the number of samples that are needed to calculate even a single expectation value using variational approaches, you quickly see that for quantum chemistry applications, it's enormous, and maybe even more than what would be required with advanced algorithms like quantum phase estimation. So in my expert opinion, we're still quite far from getting to the point where these variational algorithms, even forgetting about noise in hardware, which is of course really important, even forgetting about noise, we're very far from the point where they can compute sufficiently high accurate estimations for sufficiently large systems in a way that is actually tractable. We have methods that may not give sufficiently good approximations for systems that are not that big and take a lot of effort to do it. So it's one of the big problems in this line of research.
Yeah, thank you. In the always talking about scalability, the second question is, since one qubit represents an orbital, what size of molecules do you expect to model with this method?
So typically when you talk about the size of a system, there are two important quantities. One is the number of particles, and the other is the number of orbitals. You can think for now that the larger the number of orbitals, then the more accurate your representation of the system, right? Now, but in practice, what happens is that the number of orbitals, you can think of it as essentially a multiple of the number of particles, right? So, and again, like the question is correctly alluding to, then the number of qubits required is then equal to the number of orbitals. So essentially, the number of qubits scales roughly linearly with the number of particles, right? But there's a constant factor that's pretty big. So even if you want to do something as simple as, say, the molecule that I have here, lithium hydride, right? That's lithium. This is a 4-electron, I believe, example. Even then, if you want to have high accuracy, you may be looking at dozens and dozens of orbitals, right? And these are very simple molecules that we can solve classically without too much effort, right? So essentially, what size of molecules do you expect to be able to model? Very small ones, and you will not see work in the literature, either on simulators or hardware, that is going beyond molecules that have a few electrons, maybe in single digits. I think some of the largest things that people have tackled are things like water, but even then you look at an active space where you're only considering some of the electrons. So the short answer is very small ones. To scale them up, you need a lot of qubits, and we don't have them either in simulators or in hardware.
Okay, I have another one. It is related to the problems of the mean field theory with the computations in low-dimensional systems. Sorry, how do you handle such systems?
Like in general, or
no, I think in general, or I know there are other methods, not hard to Foc, to work on that kind of systems, but how the Xanadu or this codes, or how do you suggest to work with that systems?
Yeah, okay, so I'm not sure I understand the question, but I'll do my best to answer. So maybe let's separate. So if you forget about quantum computing, right, then this slide is trying to capture how people tackle this, right? Now, it's maybe not so much about low dimension, but about size in terms of the important parameters, which are, again, number of particles and orbitals. And again, to summarize, the DFT is the most widely used approach. And what happens here is essentially the cost of DFT is, again, something like ultimately like diagonalizing some system. So it's something that and the size of that system is, again, increasing linearly with the size of your system. So it's nothing too expensive in principle, but the more complicated you make these approximated density functionals with the exchange correlation, then the harder things become. But you can handle a lot of things, and very large ones. And again, like in material science, people can do this with like thousands of atoms. Right, that's kind of one extreme. But there's many strategies, and it's relatively complicated. In wave function-based approximations, then what people do is actually something very simple, similar to what happens with quantum algorithms, where you try to actually start building the wave function by populating sectors that have single excitations and then double excitations. So in like degrees of excitations, right? So you can imagine having a wave function that has only a reference state and all possible single excitations of that state. That now the dimension of that system doesn't grow exponentially, right? It grows more like polynomially. There's a polynomial number of single excitations that you can have on some reference system. And then you can then add an additional level of perturbation, a double excitation. And now there's even more. But overall, you can kind of tame the size of the Hilbert space and still do things like exact diagonalization. That's what this full CI method, if you've heard about it, that's what it's trying to do. It's going through all the excitations, but you can truncate it. So you can do CI at singles level or at doubles level. So there's a lot of things that people can do. They're all, in one way or another, an approximation. And quantum algorithms try to mimic, especially some of the techniques from wave function-based methods classically.
Okay, I have one more. It is when mapping to spin operators, which transformation is preferred, Jordan-Wigner or Braivi-Kitaev?
It depends. I think the most widely used one is Jordan-Wigner, and you'll find most work happening with Jordan-Wigner. And the reason is that the representation of states is very simple, very straightforward. And the effect that it has on observables is not too terrible. So it's simple, easy to work with, easy to understand, easy to implement algorithms, and works really well. I do know of, so one of the issues with Jordan-Wigner is that the observables do become more complicated. So if you want to, so you can kind of trade off where the complexity lies, if it's more on the state or if it's more on the operator. So Dft does, in my understanding, help you to make some of these, the overall expressions for the Hamiltonian can be simpler. In particular, they can have products over fewer Pauli terms, and that can be advantageous in some cases. But then you have to deal with more complicated methods to implement valid states, right? So it depends on the system, and depends on your application and your figure of merit. But most people still use Jordan-Wigner.
Okay, Marco, was another question. It is, what are the realistic possibilities for reaching chemical accuracy with quantum noise?
Yeah, it's a difficult question to answer,
Yeah.
but because it has many like components to it, but very little, I would say. Like I confidently say that I've put in myself a lot of thoughts in how this can be achieved, and I just don't see the way to do this. The main caveat is, and again, it's not even about noise, in my opinion. I think even if you didn't have noise, I think you would struggle to do it. But the caveat here is that, and this is maybe a common misleading statement that you'll see in some papers, is that when people simulate molecules and they say like, oh, we actually reproduce the exact value, this is done with an approximate basis set. So you're getting like the same value as you would do from an exact diagonalization, but within a very crude approximation. So it's actually not very accurate. You're actually not reaching real chemical accuracy in the sense that you're still far from the actual, say, measured value of this. And the reason is that you're working with a basis that is so minimal. So it's not fully representing all the properties of your system. So if you wanted to do realistic high accuracy calculations, you need a large basis set, which means a lot of qubits and more complicated circuits, right? And the reason that I think that not even noise is that important is that if you, again, the real challenge is computing expectation values, right? And if you look at the numbers, right? And I actually wrote a blog post that I'm happy to share, trying to explain this. Is that if you don't want to have really complicated circuits like quantum phase estimation, then it becomes really complex in terms of sample complexity to estimate expectation values efficiently. And especially in variational algorithms, you need not only to compute that for the final answer, but you need to optimize the entire circuit. And to optimize it, you need to either compute the cost function or compute some gradient that depends on the cost function, which itself requires computing expectation value. And you need to do that many times over all the parameters. And the number of parameters grows with the size of the circuit. So it quickly blows up. So these algorithms, they don't scale well. They don't scale. And that scaling gets even worse if you have more qubits, right? So we're very far from reaching chemical accuracy. And if you add noise, then forget about it, right? There's probably no amount of error mitigation that's going to save you, especially as things scale. So our team has a long-term vision on this. Like if we want to really unlock the power of quantum computers, and we place our bets on quantum chemistry as being the most likely area where quantum computers have some possibility of giving us performance that we can not already achieve with classical methods, it's going to take a lot of work. Right? But eventually, so I think with quantum noise, it's not going to happen. I think you're going to need support for it. But we'll see.
I have the last question. Is, do the algorithms employed are faster enough in solving hard problems as the electronic structure to overcome the limitations that the coherence might create?
Yeah, I guess it's similar to Marco's questions. I don't think so. I don't see it. I don't see it. Essentially, the bar of chemical accuracy is very high, and the size of circuits that we need to realistically have accurate calculations is very big, right? and the complexity of running the algorithms is very high, and even small amounts of noise quickly take you away from the accuracy that you need, right? So we're going to be able to do a lot of amazing experiments and a lot of like great results and a lot of progress, but that bar of really solving hard problems in a way that's truly comparable with like our best existing solutions, it's going to take a long time and a lot of effort.
Okay, thank you very much, Juan Miguel. We want to thank Marco, Felipe, and Subhadra for the help in this session. And we want to thank everyone who's watching these videos in YouTube too. Some of the questions came from the YouTube presentation. So, thank you very much, Juan Miguel, and thank you to Shanadu too. I think there are some people who are interested in trying the Python interface. So maybe you can get some contact from people around here. Thank you very much. Okay, thank you very much. And Felipe.